Good evening, everybody. Tonight we have kind of a, shall we call it a standard problem, where we're trying to find a remainder of a super large number that's you couldn't compute it manually. Now, just to show, I'm going to write it like this. We've defined S this way to be the squares here, the sum of the squares starting with 81. 9 squared is 81. Of course, 10 squared, this is 11 squared right here, right? And so you can see it ends at 630 squared. And of course, 630 is one less than 631, which turns out to be useful here. Now, but what we're trying to do right here, it says find the remainder when S is divided by 631. Well, another way of stating this is we're trying to find R mod 631. And mod 631 is equivalent to just finding the remainder when you divide a number by 631. Now notice if you divided 400 by 631, you get a remainder of 400 trivially, right? So, this is going to be a much larger number. Now, what does this really mean? You get S is equal to, you can rewrite this, remove this triple with doubles, and you get S is equal to R plus some multiple of 631, and we'll use M to be any integer. Now notice the case M equals 0 would be like what I just told you. You can have a smaller remainder. The remainder is going to be smaller, but M could be equal to 0. Okay. Now and again, I will say this at the risk of belaboring the point. There's no way you're going to compute S. Right, it's pretty amazing already, isn't it? Just 630 squared is big enough to where you'd have a hard time, But this is a bunch of numbers here added up, and the numbers are squared, right? So we want to find a remainder when we divide this unpronounceably large number by 631. Okay. Now let's move along. Now this is a very well-known result. It gets used in calculus a lot of times when you're doing the integral definition, the sum of the limit of the sums definition of the definite integral or Riemann integral. Now, just as a sanity check, let's take a look at just a very special case, n equals 1, okay? Well, what does that really say? That says that 1 squared, this is trivial, but it's sort of I've heard people call it sanity check. This would be 1 times 2 times 3 divided by 6. Which is, of course, equal to 1, right? And again, it's very easy to verify for 1 or 3. But this is a result that holds. You can prove it by induction, but this expression right here is always going to be an integer, all right? And again, that's not completely obvious, but this the way this number is arranged, you have even. If this is even and odd, so you can do a parity argument to show that 6 is a multiple of the numerator. Okay. Now the result holds for all natural numbers. That means all positive integers. Now what we're going to do is notice that 631 happens to be a prime number here. So we're taking P to be 631, excuse me. Now for this special case, it's not really super important that P was prime, I don't think, because maybe it is theoretically, but notice that when we substitute n equals P minus 1, remember this says for all n, well, P minus 1 is an n, right? It's a natural number. See how we end up with this statement right here, P minus 1, P 2, P minus 1. And again, that's exactly what you get when you substitute P minus 1 here, here, and here. Okay? Now, so here's what we end up with, all right? We got here, okay? Now notice that S is defined the way it is, right? S starts at 81, so we got to pick up the other squares. In other words, this one would be what, 64, right? So we have to pick up the other squares in order to utilize the formula. Remember, S starts at 9 squared. This is 8 squared right here. So we know this much is true just based on the formula, right? Now notice we catch a break right here. 630 divided by 6 we don't really catch a break. The formula ensures that it's always going to be an integer, but just a manner of speaking, I guess. So that's 105, right? So you see, you can really see that it is an integer. See how you have the 105 right here that I wrote? Okay. So now another really special thing that happens right here is that any number that's congruent to 0 mod 631 is a multiple manifestly, and that's what this says. You have a 631 sitting here right in your face. So that means this number is just 0. Some people struggle with that just a little bit. I remember when I first learned modular arithmetic, that seemed to bother me a little bit, but it's another way of saying if you're congruent to 0, a particular moduli, that's another way of saying you're a multiple of that moduli. Okay? So anyway, this whole part's equal to 0, and this is just rewriting it. It's nothing changed right here at all. This whole part is just 0, so I just got rid of it, right? So what we have is this statement right here. Now you can reuse this formula, or you can just add up all of these up, and you get, this is 204. 204 plus S is congruent to 0 mod 631. Just like that, folks. And again, this would be coming from the formula 9 times 10 times 17 is what would happen. If you put 9 times 10, you'd have 17 here. And that ends up being 204. Okay, now remember, what does it mean to be a remainder in a modular arithmetic context? It means S is congruent to R, where R is some number between 0 and 630. I didn't write that down. It's a remainder. Okay, so to make this a little more convincing, you could rewrite this as S is congruent to minus 204. Right, just bring it over. You can treat congruence like equality. All right? But remember, the remainder has to be a positive number, right? When you divide by a positive number by 631, you're going to get a positive number, right? So just all you have to do right here is just observe that this is congruent to 427. Now, some people just hate that when people say just observe. But notice 427 minus 204 is 631. And if you think about it, they're just that far apart. This number is 631 away from 427. Okay? So this would be our answer. This is mod 631. 427 is the answer. Okay. Now, you could say, well, why didn't you just put 427 here? You can. You know, you can just say, and you know you have it, right? But this is just a little more explicit to write it as a congruence, you know? It's just because this is what we mean by remainder. Remember, this means that S is equal to 427 plus some multiple of 631. Right? But that's exactly what we mean by remainder, right? When you divide 631 into S, and we have no idea what this multiple is. That's the beauty of modular. It'd be hard to compute this unless, you know, I mean, we don't know what M is, but its existence is implied by modular arithmetic. Okay. So anyway, 427 is the answer to the problem, and I like modular arithmetic. All right. So let me write this down right up here. The answer is 427. Again, y'all, still even after all this time being familiar with modular arithmetic, it's still amazing to me that if you just take a breath here to realize how big this number is, right? 81 plus 100 plus 121, you're already to what? Is that 210 or something? Okay. And then you're adding up these huge squares, you know? I mean, it's just amazing how large this number is. Super, super big and would be impossible to compute by hand. But modular arithmetic gives us a clean way, along with this result here, which requires some proof, of course. You know, it's an induction proof. We use that modular arithmetic to get the remainder without really ever having to do any intense calculations. Okay, so that does it, folks. 427 is the answer I got. Thank you for viewing.